Number 2, 64 feet per second. Number 1 was 48 feet per second. Number 4, he was a little more fun. He might have used a derivative, I suppose. 128.16 feet per second. 128.16. Huh? Wait, do you guys not check the odds on that?
Number 3 was 96.
Silly goofs. Yes, I am.
Okay. Oh, wait, what was...
You should already have your forever memorized, so I'm going to
Well, oh, you guys need last year's forevers. Is that what you mean?
I haven't memorized this, Pete.
Yeah. And your forever cards.
What's the IBT?
IBT.
Okay.
Intermediate value theory.
Wasting time. Shh. Let's stop. I will put on my list to share with CalcBC last year's notes. I didn't delete it. I just, you know how it kind of changes from year to year? So I need to share, what was last year, 2016-17? Forevers with BC. Alright. Thanks, Katrina. You guys got number 3, got number 4? Okay. Now we're going to number 10. Number 10, final answer is 5. Number 10, final answer is 5. Number 28. Okay, wait, guys, there are odds in the back of the book. There are odds in the back of the book.
Sometimes I forget.
That's your job, though, to have ready when you come into class and already have odds graded so you know what questions to ask me, yeah? Number 28, final answer, -1/4. Ooh, algebraic confirmation. That sounds snazzy. -1/4. Number 42, and then 44. 42, final answer is -1.
44 was the
Oh.
Did you have 40?
No, 44. I'll tell you.
44 was true, false, false.
Wait, why did it fall?
Which one?
Hold on, grade it first, grade it first. We'll come back to it. True, false, false. That was A, B, C. D is true, E is true, F is true, G is true, H is true, I is true.
What?
Number
H
60.
is true.
You can ask questions in a little bit. H is
H
true, I is true.
So it's getting close.
Number 60.
Number 60?
Number 60.
What one? 60. I is true.
Graph. The limit from both directions is 0, so the limit is 0.
It's 0?
For C, but could be I think.
Wait,
Oh wait, what?
is it 1? No, you're approaching -1.
I know the whole have 1.
Oh, C is 1. You're approaching -1.
Oh, C is 0.
You're approaching -1. And as you approach -1, that's the intercept, right?
Yeah.
But there's a hole there. So it's that the function does not exist, but the limit agrees, and the limit is 0. Is it a piecewise? Maybe the function did exist, but somewhere else. Number next one.
That's the last one. That's the last one.
Oh, cool team. So let's go ahead and get the homework assignment back up. I did hear that we had a few questions on number 44. Is there anything else you guys want to look at? 28?
Number 4. No, it's
Okay.
It was number 4 that is special.
Number 28, number 44. What was the other one you guys said? 4?
41 is special.
Oh, yeah.
Anything else? I have 28, 44, and 4. All right.
But I mean, that's special. Can I do 44?
Oh, you guys want to take them on the board? You can if you want.
I thought this was. You want it? You don't have to.
I was going to pull it up.
Oh, then never mind. Just give Corey the credit. Thank you, Caroline.
Those are the questions on 44. There was A through H. No, A through I. Do you have particular letters that you want to see?
G.
I got it. C.
I. Anything else?
C. I can add D.
Anything else?
D.
D.
I won't take on any of it.
C and same here. Yeah, I'll take on any of those.
They have a challenge.
So we have 4, we have 28, 44, we have these ones. Now, if you guys can show work, I would love you to go to the board, but if you can't show work, it's not going to work my well.
Oh, 44 is just looking at it and then saying yes or no.
Yeah.
I don't
Then
know
do
how to
give you
work.
a
Okay, so
graph.
44 let me take, because if it's look at it, I want to get the picture up on the board, and I'll take 44. Do I have volunteers for 4, 28?
Whoa.
Who hasn't gotten one yet?
Katrina's a liar.
Number 20.
Filthy liars.
I still did
Oh, thank you.
I still got 20.
This is a democracy.
Last week.
Oh, no.
Alright, Katrina, what do you want?
28.
Okay. Who else hasn't gotten one yet? Speaks, you haven't gotten one. What do you want? 4? It's yours. Go erase the board wherever you want to go. Both of you guys go to the front of the room. I'm going to pull up 44 so we can look at it. I'll give people who haven't gotten points yet first dibs, and then if we did have more questions, I would hand out to those who've already gotten one. Caroline, what's your question, Carolyn?
So, the answer was with the decimal.
Okay.
There's also the algebraic confirmation. If you get the answer without the decimal, is that the same as wrong?
That's what I meant.
Like, what, did it have a square root?
No, like it was. I still got like 1.8 because like I just plugged the number into the formula. But like the first answer that they give you before they confirm it algebraically has a decimal.
Then that would be okay. You just did it a different way.
Okay.
Yeah. Where's number 44? Don't do it now.
Did you just do the?
Oh, one more. Oh, was it one of those nasty graphs, you guys? You got tricked?
We got
Oh.
tricks. We got bamboozled.
We got trigged.
That's not trig though.
Thank you,
It
Lucy.
really isn't.
Lucy liked it.
Wait, when it wasn't true, it was limit.
Go with my joke.
Okay. Different C.
Oh, and then we derive. Okay.
Did I get them all? C, D, H, and I, or was there a math?
Could I point it out?
Was it 1?
Hold on. Did I get them all? C, D, H, and I?
Oh.
C, D. Oh, it was G and I. You guys didn't even have the right letter. Oh, let me do H too?
You could just do all.
Oh my goodness.
Just looking at it.
You guys. It's okay. Corey's not finished.
Sorry.
Alright, people at the boards, your question was later on in 44 then.
Mine was I.
Okay. So let's go over C, D, G, and H, and then Katrina should be ready for them to go over I. So C, the limit as x approaches 2. Ah, you guys got stuck by the most common mistake. Noah, explain to me what it is and why.
It does not exist because the limit as x approaches
False.
It's false.
Corey.
It's false because they're approaching the same place. Even if the
limit is
diner's
1.
closed, they're still approaching. It's 1.
It's 1.
No, it's not.
No, it's not. Yeah, it is.
It's 1.
It's
The
1.
limit as x approaches 1, right?
No, it's
No,
not.
No,
that's
false
two.
is 2.
Wait, if it's false, do we have to correct it?
No. Wait, what do you mean?
How do you say it's
That's the
false?
problem.
Or do we have to correct it?
You have to correct it.
No, it didn't say.
It didn't say
Okay.
correct.
Say what it's for.
For our understanding, we are correcting it now. So, C is false. Great. Put in parentheses because the limit as x approaches 2 of f of x is 1. As you approach 2, the limit does exist. That's why I stopped you. The limit does exist and it is 1.
I was looking at the one.
What were they trying to confuse you by? What is that 2?
F of 2.
F of 2 is 2, but the limit as x approaches 2 of f of x is 1.
Because
Alright, D. Corey.
D is true. Because if you go.
How do you describe this? How would you explain this to someone?
Because it's coming from the left, and as it approaches from the left, it equals 2. Even though it's not, even though there's a hole there, it's still coming from the left at 2.
So as we come from the left of the function, remember it's all about the approach, and even though the hole is there, just like Corey said, even though the hole is there, the left side is approaching 2, so that is true. Letter G. Tom. Corey. What's G? True or false?
True.
True?
That's
How
true.
come? 0 0 from below or above. What's going on? Where's it approaching? Yeah, it meets and they're headed the same direction. Good. So 0 from below and above, they're meeting and they're headed the same place. So no matter what would the limit be?
0.
Good, Tom. Corey, H.
So the reason H works is because since they're just regular brackets, that means not at -1 or 1, so even though there's a hole, it's all the values that's less than 1 and less than -1, and since it's all connected, it's all good.
You're only looking at these
Yeah.
values, you're not looking from
Not
above
exactly
1. Good. You're only looking from below 1. So, all the limits will exist as you come from this direction. Yes, the limit exists. It approaches 1. As you come in towards, like all of these, the two sides are agreeing. This one, the limit exists as you come towards 1 from below. You were not supposed to look anywhere beyond the numbers in between and not including. Hence why that one's true. Last but not least, I. Do I get that one? Tom's done it, Corey's done it, Noah's done it. Gabby. What's I?
I put false. 1. Because there's a whole.
That's
Okay. Hold on, wait. No. We need to hear that though, right? The reason a lot of people would say false, and that would have been probably the most common, one of the most common mistakes out of this whole table, is you see a hole and you're like, no! The function is not continuous. But since it's a limit, what would you say now? Because? What's the limit as x approaches 2? 1. The function is at 2, but the limit is at 2. Corey, do you have anything to add?
The two-side limits agree.
The two one-sided limits agree. And remember, this limit agrees. Once again, some of you might have gotten stuck at 1. But look, we're only looking at the numbers bigger than 1. We're only looking at the one-sided limit from 1, the one-sided limit from 3, and everything in between. So we're good. And technically, I guess, since there aren't brackets, you're not even looking at 1 at all. You're looking at 1.00. Well, 1.00000001. You're looking at that one. But all of those, the two-sided will agree. There's no jumps. There are no breaks. No asymptotes. The only problem is a hole. And is a hole a problem for a limit?
I have a question for 28. Could you tell the hospitals?
Yes. I personally wouldn't have liked it. I personally would have liked the algebraic better, but that's just me personally. You could have done it. You would have, because when you plugged in, you do get 0 over 0, right? You would have had to use a quotient rule, or you would have had to place 2 plus x to the -1 and done chain rule, which wouldn't have made a big difference. But you still would have had to simplify the complex fraction.
Oh,
Did you do L'Hopital's?
yes.
This would equal for L'Hopital's? Right? And then you would have plugged in 0. 2 plus 0 is 2. 2 squared is 4. -1, 4. Does that make sense?
Mm-hmm. Okay, I see what I did wrong.
Okay.
I messed up.
But otherwise, what Katrina was doing was simplifying the complex fraction, and eventually, in these algebraic, if you do have an algebraic way to go, if you have an e to the x, you're not doing algebraic. If you have a trig, you're not doing algebraic, right? But if you have algebraic, you can go and simplify with, multiply by the common denominators of all the fractions within fractions. I need to think of a better way of saying that. Fractions within fractions, but 2 minus 2 just cancels. You always have a reducing. This step right here is key. Then plug it in together. And then find the speed. What speed the same thing as?
Distance over time.
Right? You can think of change in distance over change in time. When they say at 4 seconds, you're not thinking of change in distance. Aren't you thinking about dt over dt? The derivative of distance with respect to time? Yes. Okay. Sorry, I was just saying right, and I was going to say make it positive. So you can think of, since you guys do have a background in calculus, you could just take the derivative, you could plug in, just make sure it's positive at the end, give yourself an answer. So,
Could I just put inner denominators?
So complicated. I don't
Inner, though, I like chain rule, how inner is in the argument. You know what I mean? So that's why I'm like, I don't know what is inner. I think like entrenched, that's not a good word. Inscribed, I don't really like that one either. Like, if you guys think of a good way of saying the denominator within the denominator. Huh? Innermost. Like, it makes sense until you do compositions, but all my classes, they're doing compositions of functions, and I don't want the innermost to be confused with. I just haven't never come up with a great way of describing it. Okay, boop. Kiddos, section 2-2, let's go. We already started. We have some more work to do though. Remember, this is the one I let you guys get creative with on Friday. Some of you liked that, some of you.
I had fun.
It was an adventure though. And you guys got down horizontal asymptote, okay, right?
Yeah.
Horizontal asymptote exists as long as the limit equals a constant as you approach infinity, negative infinity. We talked about squeeze theorem and how it's complicated as you're going towards a constant, but it's much simpler, at least with trig functions, as you're going to infinities. So I showed you one application of the squeeze theorem as you're going to infinity of a trig function. And I should probably qualify that just a little bit, of restricted trig functions. Too obvious. Okay, so restricted trig functions like sine and cosine. Tangent, is that going to be super helpful as I go to infinity? It's just going to be infinity, right? Or it's going to be DNE because it oscillates. Anyway, that's going to be a bit more complicated. Do you guys, we got to this page and I was like, hey, you need to write it. No, we know if we have something like e to the x plus sine of x, we know to plug into e to the x, plug into sine of x, and think about them all together, but we plug in separately, right?
Mm-hmm.
You don't have to have a great picture of that. Same thing with subtraction, multiplication by a constant. Now, can you, though, looking at these and with your background in differentiation, can you tell me which of these are mimicked in the properties of derivatives, and which of them are not?
1 and 2.
1 and 2, definitely. 4, definitely.
4.
Is 6?
No.
1 and 2 and 4.
No.
Not 3, not 5, and not 6. True? And 4. 1 and 2 and 4 are mimicked in derivatives. And we could go and break it down, the definition of the derivative as a limit, and see why it works the way it works. We might not though. Okay, anyway, the properties are there. Let's keep going. Ready? Set. Okay, well, pause. You could write this whole but what have I done for you? Take f as 5x plus sine x. Hey, look, he's right there. And g as x. Oh, look, he's right there. Do the limits as x goes to infinity, look, right there, exist. Can we apply the quotient rule? Explain. So, you don't have to write all of this, but I do want you to write the problem and then read and see, how would I answer that question? So you can dig just a little deeper. So funny, for a book that's so small, it has such a
Oh, he's gonna.
Not yet. Think through 1 and 2 and 3. Oh, easy. We're supposed to get Gerardo's letter. You were not in the class. Kiddos, tomorrow, first thing in class, I'm going to have, tonight's busy, I don't know. Anyway, we have some things to talk about. I'm not sure if I'm going to have your full parametric graded. I got pre-cal's graphic calculator quizzes graded. I got all of your summer quizzes graded from AB and BC. It was quite a bit of profit.
Was it not a good day?
I didn't quite get, huh?
Was it not a good day? Did we do bad?
You guys didn't specifically, but there was a lot of markings I had to do amongst all the pre-cals and all the pre-cal and then AB.
But not the BCs?
BC.
Oh, good.
But I haven't gotten the fuller paragraph.
Not the full paragraph?
What's in my copy? It's a little longer.
Wow. You're so cool.
Alright. Number 2 is asking something similar, but it's talking about the sum and difference rule. Number 3 is something similar. And number 4 is its own little summary of 1 through 3. Was this Trina who was asking about the card function?
No. No.
Wait, no.
That was Corey.
I didn't ask.
Katrina was
She asked, "Do you guys want to hear the story?" And I'm like, "Yeah." She's the one who asked if we want to hear the story.
It was
She told them it.
Okay.
It was a great
Yeah,
story.
it was
I
really.
almost passed out this day.
I love dog.
Well, it makes me queasy. and not good.
That's true.
You guys should have lunchtime story time with Doc, and that way any stories that come up in class, you can write them on a post-it and say, "Can we come talk to you about these later?"
But that's how we do it in class.
No.
She's so interesting. I love talking to this.
Okay, so on number 1, let's see what you've gotten. We'll slowly go to number 2, slowly to number 3. Number 1, we have 5x plus sine of x over x going to infinity. Do the limits as x approach infinity of f and g exist? What would you guys say? Does the limit of f exist as you go to infinity? No, you're right. It doesn't exist because you have infinity plus. Well, hold on. So infinity, bigger numbers, plus 1 and negative 1, 1 and negative 1, 1 and negative 1, 1 and negative 1. Is 1 and negative 1 really going to take away from your infinity? Oh. So does the limit exist?
Yes.
Interesting. The limit of sine does not exist, but the limit of 5x plus sine exists. And it equals infinity. What's x? Infinity. What is the limit?
1. No, 5.
How would you check this?
On the top and bottom one, right? Can you do that? If top wins, it's infinity. If bottom wins, it's 0.
You could say the strongest, right? The strongest out of 5x plus sine is 5x, true. And the strongest from the bottom is x. So do we have a way of approaching this? Yes. Could you always throw it in your calculator and look at the graph, or look at your table? Yes. You could, and then you should see it leveling off at 5, right? But is there going to be oscillation as it levels? Yes, there's going to be oscillation.
Would it work with like the denominator is x and the top x, and if it's like square? Well, I don't know what it's called.
Degree test.
Degree test.
Is it tied? Yeah.
Yes. So the sine of x doesn't affect the degree.
Well, the sine is not the strongest.
Okay.
So since the sine is along with the 5x. But does that pose some problems with our theorem on the page before? Well, how do we take the limit of f? Don't we take it a piece by piece? And that would be infinity plus dne, so wouldn't we just say dne, we can't do it? That's where the dilemma lies. Number 2, has anybody checked in your graphing calculator? Someone. Jason, check in your graphing calculator for 1.
Check on your slide.
Number 2, pause. Can we apply the sum rule?
Yes.
Yeah.
Okay, what's the limit as you go to infinity of sine squared? Squared of sine. So what's the limit as you go to infinity of
1.
sine squared? What's the limit
1.
of sine? 1 to negative 1, but it's squared.
1.
So 1. Wait, so what's the limit of cosine squared?
1.
So 1 plus 1 is 2?
2.
But that's not the limit. What is it?
1.
Trig rules. Sine squared plus cosine squared is 1.
That's a thing.
Yeah, first forever card. The Pythagorean identity. So wait a minute. If we tried to use f plus g, and if we tried to take away the squares, uh-oh. I got 2, and 2 is not 1. Struggle. Number 3. Find the limits as x approaches infinity of f and g. Can we apply the difference rule to subtraction? What's the limit as x goes to positive infinity of ln of anything, basically? As long as it's not absolute value. Infinity, right? Minus, what's the limit of ln of x plus 1? Oh, well, wait a minute. Oh, infinity minus infinity is 0, right? Check it in your calculator. I'm not going to tell you this one. Go. Yeah.
Did you want to simplify? Did you do like log system where like 2x over x plus 1 and you give e to that? And then just plug in the infinity and figure that out?
I was gonna go there, but you beat me. That's okay. I'll go.
Why? How do you get? I don't know how you got it.
Oh!
Oh, because the coefficient.
Oh my goodness! Oh wow!
And top one, they're tied. So it's
Now, LN2 is going to be a decimal. Those of you guys that are in your calculator, how can you check that we're measuring up? Can you go to your table? Pause. Pause. Can you go to your table? How do you approach infinity in your table?
Just keep putting bigger numbers.
Bigger. So I could do like 100. I did 1,000. I did 10,000. And like a million. I had 0.6832, 0.69305, 0.69315. I'll do some more zeros. 0.69315. Guess what LM2 is?
0.69.
0.69314718806 and 15 is then rounding. It's LM2. Now, question. I went ahead and used the quotient property of logarithms. Hold on. I used the quotient property of logarithms. Then I used the composition property, which says f of g, you can take the limit of the inside and then apply the outside. So the limit of the inside, weren't the degrees tied? So it's 2, apply the ln, and I got it. Look at number 4. What advice might you give about applying theorem 5? In one way or another, if we had strictly followed the properties with each of these functions, we would have gotten a wrong answer. 1, we might have said DNE. 2, we might have said 2. And 3, we might have said 0. Well, technically it's indeterminate, but either way.
Don't do it with fractions, trig, or natural or logs.
What do we need to beware of?
Trig, fractions, and logs.
Transcendental functions and trigonometric functions. We have to beware of ln. We know we have to beware of exponential. Remember how going to positive infinity of exponential, that's the strongest. Going to negative infinity, it's the smallest. We got to beware of logarithmic, exponential, and trigonometric functions. Yeah.
For the first one, would you have like done like the part method and then just the x's on the polar 5 would cancel and then the sign would go?
It's ultimately the degree test, but yeah, you could have done 5x over x, which is 5. Sine over x, who's stronger, sine or x?
Isn't that
Add? No, x is stronger, so it's 0.
But you could have split it up, and 5x over x would have been 5. Sine over x, well, sine's stuck. X is not.
So 0.
Now, are we technically doing math with that?
Yeah.
Technically, we'd have to go to squeeze theorem if we wanted to prove that this is true. We wouldn't be able to outright apply our properties. I'm just telling you, squeeze theorem, between 1 and negative 1, we can deal with sine of x over x as a polynomial expression and not as a trig expression. So long story short, we have to be very careful with trig, especially constrained trig like sine and cosine. Because squeeze theorem would help us make these jumps that I'm making in a much less formal fashion. But be careful how you apply the properties to those types of functions. Does that make sense, guys? Was that one kind of tricky, this one especially?
No?
I didn't have you convinced that it was 2? Not even for a second? Okay, infinite limits. You guys see how there's more depth in this one, though, right? Yeah. And more possibility for depth. Like, we're not going super deep, but we're just going over a few things where it's like, what we learned last year gave us a great introduction to how to apply calculus. But it didn't give you a great introduction to how all of the calculus applies and works, the behind the scenes, or the proofs for why each of the things that we did were true. And that's where, in some of these areas where we're going to see weaknesses in the sense of maybe applying something without going deeper and saying, wait, can I actually apply it? When can I apply it? We don't have that proving background, which is why I was saying even after taking Calculus BC, if you are going to go on, specifically in math, not necessarily in engineering, like an honors math program, it might not be a bad idea to start with the second calculus. You will have seen sequences and series. You will have seen the core foundation of what you need to do. But it's good to hear a college professor's perspective on the how and the why and the proving and the pure math. That honestly is not my background or my strength or even my perspective. Okay, you guys are writing about infinite limits. Limits that do not approach. Not limits as x approaches infinity or negative infinity, but limits that equal infinity or negative infinity or DNE as x approaches a constant. Now, why do you think, last year we didn't even go into this much depth. Last year we said if any limit has any sort of infinite answer or part, then a vertical asymptote exists. Why was it so particular to say, hey, the one-sided limit and the two-sided limit, and to separate them? The one-sided limit from the right, the one-sided limit from the left. Why do you think those need to be separated? Why not just say the limit is infinite at all? Yeah, they're different. If they're different, the limit does not exist. So we say, oh, the limit is infinite or does not exist. Well, not necessarily. Aren't there different ways of not existing? So to be as concise and as complete as possible, you do have to state if either one-sided limit has any sort of infinite answer, positive or negative, then there must be a vertical asymptote. So as you guys look at number 1, we know to plug and chug, right?
Yeah.
And as we plug and chug, what's sine of pi over 6?
1/2
Over 0. What is this supposed to point me to? Check sign. Infinite check sign, right? Number over 0, we know it's infinite. We need to check the sign. How do we check the sign? Remember? Sine of pi over 6. Negative. Remember how we did notation last year? If we're coming from the low, what's sine of pi over 6 right before pi over 6? Positive or negative? It's still first quadrant right before, right?
Yeah.
So that's going to be a positive. But what's something a little bit less than pi over 6 minus pi over 6? Negative. Uh-oh. So as we come from the left, what do we have? Remember how we did this? Negative infinity. Now, as we come, as x approaches pi over 6 from above, you have to think about the unit circle again, but the angles right above pi over 6, aren't those still in the first quadrant? So the top will still be positive. We're still in the first quadrant. All the signs are positive. But in the bottom, what do we have? So positive over a positive. So then what's my overall limit? But since at least one of the one-sided limits had an infinite answer, yes, there's a vertical asymptote at x equals pi over 6. Does that make sense, guys? Because you also remember how to determine one-sided limits when we have infinite answers. Think about the value a little bit below, a little bit above. With trig, I don't know, my brain goes to a graph and I say, oh hey, sign's above that entire time, even before and after pi over 6. Alright kiddos, we've done a lot. I'm going to give you a challenge. Oh stink, it stopped, so I have no idea how much time we have left. We have at least like 1 or 2 minutes.
It's 11:59.
No, it's not. Isn't it 58?
Nope, it's 59.
According to the school or according to your watch?
According to my phone.
Pause. There's one thing, I still want this homework due tomorrow, but there's one thing I'm going to challenge you. Let's get the book just a little bit. There's something that's new, and yet it's not. It is the foundation for our degree tests. It is the foundation for why the degree tests work the way they do. And it's called end behavior models. End behavior models. We talked about end behavior in pre-calc, where it was basically like, hey, are the ends of a graph leveling off towards a horizontal asymptote? Are they going forever up? Are they going forever down? I want you, when you get there in homework, to look in the book, maybe look at some examples, and figure out, ooh, caught somebody. End behavior. It's okay, I'm just ignoring. End behavior, no time to stop. and behavior. And behavior has you think about things like, as x goes to infinity or negative infinity, which portion of this function, some sort of linear combination that's adding or subtracting, multiplying, dividing, who takes over? Who is strongest? And it gives us the basis for the degree test. So, kiddos, homework number 4 due tomorrow. But come in ready to discuss and behavior. So I'm going to start there, take some notes on it, what you guys learned, and then we'll see how
Hair.
it's going. Bye, guys.
Ate it.
Bye, guys.
Tomorrow.
Hello.